At 1:30 a.m. on the 1st of June 2009, an Airbus A330-203 cruises at 35,000 feet above the southern Atlantic Ocean. The aircraft departed from Rio de Janeiro at 10:30 p.m. and is about 3 hours into its 10.5-hour flight to Paris Charles de Gaulle Airport in France. On board the Airbus are 216 passengers and 12 crew members. The aircraft has just passed a navigation waypoint known as Intol, which sits about 300 miles off the Brazilian coast. A navigation waypoint is a known reference point with a given set of coordinates. It is useful for both the air traffic controllers and pilots to monitor the progress of an aircraft, especially when radar coverage is not available over the ocean. The captain of the aircraft makes contact with the Atlantico Area Control Center, responsible for controlling air traffic in this particular region of the southern Atlantic. The captain advises Atlantico that they have just passed the Intol waypoint, and their next waypoint will be Salpu in about 15 minutes, followed by Oraro 15 minutes after that. The Atlantico controller advises the aircraft to contact Dakar, the next area control center on the aircraft's journey, after passing a further waypoint, Tassil. The pilots ask the Atlantico Area Control Center to perform a test on a piece of their radio equipment. With the check successfully completed, the crew are advised to maintain their altitude of 35,000 feet. The captain acknowledges the instruction and signs off. It is the last time anybody will hear from the crew of the Airbus A330. What has begun as a routine flight across the Atlantic Ocean will become one of the most lengthy and complex air accident investigations in history. You are listening to Inside the Black Box. This is the story of Air France 447.
Pull up! Pull up!
After completing their communication with Air France 447 at 1:35 a.m., the air traffic controller at Atlantico contacts Dakar Area Control Center. The Dakar Control Center, sitting in Senegal in the northwest of the African continent, will take over monitoring of Air France 447's journey from waypoint Tassil onwards. Waypoint Tassil sits on the boundary between Atlantico and Dakar's area of control. The Atlantico controller advises his colleague in Dakar to expect Air France 447 at waypoint Tassil at 2:20 a.m. at 35,000 feet, travelling at Mach 0.82. As the Atlantico controller is relaying this information, the controller at Dakar interrupts him and says he will need to call him back. 10 minutes later, at 1:45 a.m. as promised, Dakar contacts Atlantico requesting information on Air France 447's proposed route. After Atlantico relays the flight's information, the controller in Dakar creates a virtual flight plan in his air traffic control system, which tracks the expected progress of the flight based on the speed and direction that has been input into the system. 1 hour later, at 2:45 a.m., Dakar contacts the next area control center along Air France 447's route, SAL, on the Cape Verde Islands, to prepare the handover of Air France 447 to the next area of control. Air France 447 is scheduled to pass the waypoint which marks the beginning of SAL's control area at 3:45 a.m., 1 hour from now. The Dakar controller informs the controller at SAL that he has not yet heard from Air France 447. However, this is not unusual and not a cause for immediate concern. A number of factors, including atmospheric interference, could lead to a loss of contact between the aircraft and the controllers. More than an hour passes. At 3:54 a.m., 9 minutes after Air France 447 was supposed to enter SAL's zone of control, the controller at SAL contacts the Dakar controller via telephone to confirm what time Air France 447 would be passing into their zone. The controller at Dakar states he believes it was at 3:45 a.m., but as he has not heard from Air France 447, He would now make contact with them to confirm. The Dakar controller tries several times to contact the aircraft, not receiving any response. For the next hour, the controllers at Atlantico, Dakar, and Sal communicate with each other, trying to determine if they've had any contact with Air France 447. They request that another Air France flight, which was slightly behind Air France 447, Air France 459, try to make contact. Air France 459 also fails to make contact with the aircraft and informs Air France's Operations Control Centre in Paris of the situation. The Air France Operations Control Centre is also unable to establish communications with the aircraft. After the various discussions between the area control centres along the flight path, one thing becomes clear. The last radio contact with Air France 447 was 3 hours ago at 1:35 a.m, and the last radar contact was about 15 minutes later. No communications have been received from the airliner since. At 5:23 a.m, the Atlantico controller contacts his associate at the Aeronautical Rescue Control Centre, informing him that they do not know the position of Air France 447. An entire 3.5 hours after the last contact with the aircraft, the search and rescue operation begins. The exercise initially involves gathering data on the takeoff conformation, the aircraft's flight plan, fuel reserves, and radar trajectory, among others. At 11 a.m, about the same time as Air France 447 should be running out of fuel, the first rescue helicopter launches from Brazil to search for the missing aircraft. An hour later, and on the opposite side of the Atlantic, a French Breguet Atlantic coastal patrol aircraft takes off from Dakar and is put at the disposal of the Brazilian authorities to search for the missing airliner. On the evening of the 1st of June, the BEA, responsible for investigating accidents involving French aircraft occurring in international airspace, dispatches a team to Brazil to begin gathering information. Air France issues a flurry of press releases, confirming first the disappearance of Air France 447, and later that there was almost no chance of survivors. Doctors and psychologists are made available to the families of those aboard Air France 447 at Charles de Gaulle Airport, who had arrived to collect their loved ones. Almost immediately, the media begins speculating what happened to the aircraft. The initial theory is the aircraft was in an area of turbulence and may have been lost in bad weather. Lightning in particular is blamed as a culprit. Since most aviation accidents occur near to an airport, or at least on land, the story captures the attention of the public in many countries because of the sense of mystery that surrounds the disappearance. One day later, on the 2nd of June, an aircraft conducting an aerial search over the Atlantic Ocean sights the first signs of Air France 447. A 5-kilometre-long band of what appears to be aviation fuel or oil can be seen from the sky. Also spotted is an aircraft seat, an orange life preserver, and pieces of cabling. The searchers can also see bodies. Over the next few days, French and Brazilian warships begin arriving in the accident area. Starting on the 6th of June, they begin to pull wreckage and bodies from the water. After confirming that these bodies are indeed passengers of Air France 447, it is officially confirmed that the aircraft is lost, with no chance of survivors. All souls aboard Air France 447 are dead. Over the next few weeks, search and rescue workers scoured the ocean for debris and bodies floating on the ocean's surface. Through the combined efforts of French and Brazilian ships and aircraft, searchers were able to recover the bodies of 50 of the 228 occupants aboard, including the captain of the aircraft, as well as hundreds of pieces of wreckage. The largest piece of wreckage the searchers discover is the aircraft's tailplane. As each component of the aircraft and body was found, it was meticulously logged in a database each day. This was done in order to measure how the debris had drifted from the initial point of impact. This was important because while numerous parts of the aircraft had been found on the ocean's surface, it would be on the ocean floor where the answers to what really happened to Air France 447 would be found. The aircraft's flight data recorder, and cockpit voice recorders in particular, would provide the investigators with the best chance of understanding what had happened. Following the conclusion of surface recovery operations, the BEA was given responsibility for the organisation and coordination of operations carried out by France for the search and recovery of wreckage and bodies from the seabed. A more inhospitable search area for an aircraft to be lost in could scarcely be imagined. Air France 447 had crashed hundreds of miles from any significant landmass. Its location was believed to be somewhere to the east of the Mid-Atlantic Ridge. Imagine the efforts required to find and recover wreckage if an aircraft had crashed on one of the world's great mountain ranges. Now imagine that mountain range is submerged under thousands of meters of water. Depths from the surface in this region range from 700 meters to 4,500 meters over very short distances. At this early stage, the best chance of finding the main wreckage of Air France 447 was to locate the signal emitted by the black box's underwater locator beacons. These devices activate when submerged in water. When activated, they emit an ultrasonic signal once per second. On Air France 447, there was an underwater locator beacon attached to the aircraft's cockpit voice recorder and digital flight data recorder. Unfortunately, there are a number of limitations with the underwater locator beacons. First, the range of the signal is fairly short given the vast area of ocean the search area covered. The ability to detect the signal is determined by the quality of the equipment used to find it. Second, the beacons have a finite battery life of about 30 days. After that battery fails, the signal from the beacons will no longer be emitted. There is therefore a race against time when trying to locate the beacons before their battery runs out. To assist in the search for the underwater locator beacons, on the 5th of June, the French Navy sent a nuclear submarine, the Emeraude, to assist in the underwater search. The submarine could use its powerful passive sonar system to detect the signal. Passive sonar involves listening for the ultrasonic sound using the submarine's powerful hydrophones. Although the system was originally designed to listen for sounds such as approaching warships above or other submarines, the system was capable of detecting ultrasonic signals up to 2,000 meters away and was well suited to the task. With further modifications, the crew aboard the Emeraude were able to extend this range to 3,200 meters. Unfortunately, the Emeraude can only travel to a depth of about 300 meters before the water pressure would destroy it. The submarine's ability to search below the surface was therefore limited to about 3,500 meters. It would need to be supported by other vessels. Recognizing that the sonar capabilities of the Emeraude would be insufficient to locate the wreckage of Air France 447 on its own, the BEA requested the use of 2 towed pinger locators from the United States Navy. These devices are essentially highly sensitive hydrophones, which are towed behind ships deep below the ocean. They are able to withstand enormous pressure and operate at depths of up to 6,000 meters. This makes them ideal for locating the underwater locator beacons on Air France 447. Each of the towed pinger locators was towed behind a ship, with the locator as close to the seabed as possible. The search using this equipment was painstakingly slow. The ships towing the pinger locators were travelling between 1.5 and 5 knots. Completing the underwater search component was the French oceanographic research ship, the Pourquoi Pas. Like the Emeraude and the towed pinger locators, the Pourquoi Pas also had sonar capabilities, and was tasked with listening for the signals being emitted by the beacons. The Pourquoi Pas was also equipped with two other invaluable pieces of equipment. The first was the Nautile submarine. The Nautile is a small submersible that is crewed by three. It is capable of travelling to depths of up to 6,000 meters below the sea. The submarine found fame when it was involved with the recovery of artifacts from the wreck of the RMS Titanic during the 1980s. The other piece of equipment was a remotely operated submersible. Both of these vessels would be used to map the ocean floor in an attempt to locate the wreckage. Over the next 31 days, the Emeraude, the Towed Pinger locators, and the Pourquoi Pas with Nautile and the ROV scoured the search area for signs of Air France 447. They used a ring which centred on Air France 447's last reported position, and with a diameter of about 65 kilometres. They covered 22,000 square kilometres of the defined search area. However, as the end of the expected battery life of the underwater locator beacons approached, and with no sign of Air France 447 found from any source, the first phase of the search for the aircraft was called off. It was now no longer possible to locate the wreckage of Air France 447 using passive sonar methods, since the underwater locator beacons were no longer emitting a signal. Instead, the investigators would need to use active sonar in order to discover the location of the wreckage. Unlike passive sonar, which works on the principle of listening for sounds generated by the target, active sonar sends out a signal, which is reflected off a target, and then measures the signal that is returned. The Pourquoi Pas was refitted with a towed acoustic sonar system. This device is towed behind the ship and sends an acoustic signal downwards. That signal is reflected off the sea floor and builds up an image of the sea floor and anything sitting on it. From the 27th of July to the 17th of August 2009, the Pourquoi Pas once again scanned the 40-mile circle, travelling back and forth. Where there was a promising sign of the aircraft, the submersible Nautile or an ROV was dispatched to the seafloor to investigate further. Unfortunately, the wreckage of Air France 447 still remained elusive, but the work was not entirely a waste. This search enabled the BEA to develop a detailed map of the seabed where the aircraft was believed to have disappeared. But with no sign of the aircraft after 2.5 months of searching, the BEA called off the mission and reconsidered their options on the search for the wreckage. In parallel to the subsea search, the investigation on what caused Air France 447 to end up in the Atlantic Ocean continued. At this stage, the BEA had limited evidence to start formulating an opinion. Some of the most useful evidence was the wreckage which had already been found. The largest component of wreckage, the tailplane, and other hundreds of pieces, were arranged in a hangar, roughly where they would have been on the aircraft. There did not appear to be any sign of fire. What the pieces of wreckage did show were signs of extreme vertical compression, as if they had been crushed. In addition, the bodies recovered demonstrated trauma that would result from a rapid vertical deceleration. From this, the investigators were able to determine that the aircraft had struck the ground in level flight, with a high rate of vertical descent. Other pieces of wreckage provided more clues. The cabin masks, deployed in the event of a depressurization, had never been used. The life jackets were still in their containers. The cabin crew's seats which had been found were unoccupied at the time of impact. All of this pointed to the passengers and the cabin crew being unaware of any problem before the time of impact. Although the last voice communication was received from Air France 447 at about 1:35 a.m., this was not the last message that the aircraft transmitted. The Airbus A330, like other commercial airliners, is fitted with a system called ACARS, ACARS stands for Aircraft Communications Addressing and Reporting System. The system is used to transmit messages and information between an aircraft and the ground by VHF radio or satellite signal if VHF is not available. ACARS is usually used to transmit three types of information: communications with air traffic controllers, operational communications between an aircraft and its airline control center, and maintenance messages between the aircraft and the airline's maintenance center. This final use of ACARS enables maintenance crews to be ready to repair an aircraft's systems as soon as it lands, minimizing downtime on the aircraft. Air France 447 transmitted a number of ACARS messages during its journey. The aircraft was programmed to transmit its position every 10 minutes, with the last position report being at 2:10 a.m. Up until this point, the aircraft had transmitted only 2 maintenance messages, both related to issues with the aircraft's toilets. However, at the same time as the aircraft's last position report was announced, the aircraft began sending a barrage of maintenance messages. Most of the messages appeared to stem from a disagreement between the speeds recorded by the aircraft's flight systems. In order to monitor speed, the aircraft utilizes a system of pitot tubes and static ports, which are placed on the bottom of the fuselage, just below the cockpit. The pitot tube on an aircraft is a small pipe which faces into the direction the aircraft is traveling. As the aircraft moves forward, the airflow travels through the pipe and into a chamber, building up pressure as a consequence of the airstream. Also connected to this chamber is the static port. This looks similar to the pitot tube, but instead of the opening of the tube facing into the airflow, it is parallel, so simply measures the pressure at a given altitude. This is known as static pressure. The difference between the static pressure from the static port and the pressure caused by the airflow from the pitot tube is directly proportional to an aircraft's speed. The pitot tubes and static ports are therefore essential for the operation of the aircraft. So crucial, in fact, that there are a total of 3 systems for redundancy. These systems are the captain's system, which sits on the left of the fuselage and feeds into his instruments, the first officer's, which sits on the right of the fuselage and feeds into his instruments, and a separate standby system that can be used in the event of a failure of the other systems. The implication of a speed disagreement between 2 systems would lead to a number of changes in the A330. The first was to disable the Airbus's autopilot and auto thrust. Auto thrust works in much the same way as an autopilot, but instead of managing the aircraft's direction, auto thrust manages the aircraft's speed. It works in much the same way as cruise control works in a car. The disabling of these 2 systems would require the aircraft to be flown manually until reliable speed readings were available again. Another significant change to the aircraft as a consequence of speed disagreement relates to the reconfiguration of the aircraft's control systems to alternate law. In modern commercial airliners, the inputs by the pilots on the aircraft's controls do not directly translate to the movement of the aircraft's control surfaces. Instead, these inputs are fed into a flight computer, which translates these inputs into movement by the aircraft's control surfaces. Since aircraft usually fly in this mode, this is referred to as normal law. Depending on the inputs made by the pilot, the computer will restrict the angle of attack so the aircraft cannot stall. It will restrict the load factor on the wings so they cannot be overstressed, and they will limit the speed of the aircraft so it cannot overspeed. But when speed data shows disagreement, the aircraft transitions from normal law to alternate law. In alternate law, some restrictions on what the pilots can do with the aircraft are removed. This can potentially lead pilots to operate the aircraft in ways it was not designed for, with higher bank angles, higher angles of attack, and higher speeds being possible. Pilots, however, are trained to operate their aircraft in these flight modes and are taught the implications of a transition to alternate law. As well as the faults relating to speed disagreement, there was also a number of other messages received in the 5 minutes before communication with the aircraft was lost. This included the aircraft's terrain collision avoidance system malfunctioning, and the aircraft's cabin indicating a high degree of vertical speed, before all messages were finally cut short at 2:15 a.m. At this point, this was all the information the BEA had on the accident. While it is quite rare that the speed indicators do disagree, it is also very rarely fatal, since pilots are trained to manage this situation. Because Air France 447 had essentially disappeared, what happened to the aircraft was ripe for speculation, even when the BEA released interim reports. Theories such as lightning, violent turbulence, hailstorms, and even hijacking were suggested. Given the reputation of the Airbus A330 as a reliable and safe aircraft, and its widespread use, there was an enormous amount of interest in the accident and pressure to find answers on what had happened. In parallel, planning for the third stage of the underwater search was well underway. During the preparatory work which took place between September 2009 and January 2010, an extensive analysis of the data from the previous phases and modelling of the structure of the sea currents was completed. This made it possible to estimate the drift of the airplane debris between the date of the accident on the 1st of June and the time of recovery from the 6th of June onwards. This enabled the search team to reduce the area of the search significantly, to only 2,000 square kilometres. 2 vessels were chartered to search the reduced search area. The Anne Candies, equipped with a towed active sonar system, and the Seabed Worker, which held a fleet of submersible autonomously operated vehicles with active sonar capabilities. The 2 vessels scoured the area in which the aircraft was expected to be found between the 2nd of April and the 24th of May 2010, but once again there was no sign of the aircraft. With the third phase of the search for wreckage being unsuccessful, and with nearly a year passing since the loss of the aircraft, the BEA needed to try a different approach. Shortly after the disappearance of Air France 447, the BEA had contacted Metron, a scientific consulting company which uses mathematical modelling to solve problems. The data scientists at Metron used a process known as Bayesian inference. The principle of Bayesian inference took into account all the prior information known about the crash location, as well as the evidence which became available over time. The result was a probability distribution for the location of the wreckage, which helped investigators determine where the wreckage was most likely to be located. The initial probability of finding the aircraft in a given location depends on a number of factors: the last GPS location transmitted by the plane, how far the aircraft might have travelled after that, and also the location of wreckage and dead bodies found on the surface once their rate of drift in the water had been taken into account. This gave an initial probability, known as a prior. The BEA had taken this information into account in search phases 1 to 3, but the result had been unsuccessful. The scientists therefore needed to update the model they were using. This is what statisticians called a posterior probability of the location of the wreckage. To calculate the posterior probability, Metron took into account the failure of 4 different searches to locate the aircraft in order to update their mathematical model. The first was the failure of searchers to find debris or bodies for 6 days after the plane went missing. Next, there was the failure of acoustic searches in July 2009 to detect the ping from the underwater locator beacons, Next, another search in August 2009 failed to find anything using side-scanning sonar. Finally, Metron took into account one more possibility, that the underwater locator beacons on Air France 447 had failed and had never been emitting a signal at all. By updating the probability map on the basis that the underwater locator beacons had failed, Metron identified areas to the north of the last known location where they believed there was a high probability of the aircraft's wreckage being located. On the 25th of March 2011, the same vessels which had been used in the previous search were brought to the area once again. This time, the searchers were armed with the information provided by Metron. They would focus on an area very close to the last known location of the aircraft. On the 2nd of April, only 1 week after the search had begun, the side-scanning sonar on one of the underwater autonomous vehicles identified something on the seafloor. Signals on the seabed, known as backscatter, were reflected up. Although what was on the seabed was clearly man-made, it was not clear whether the debris field belonged to the aircraft. The next day, the autonomous underwater vehicles were again deployed to the seabed to investigate further. There, nearly 4,000 meters below the surface, the searchers discovered what they had been searching for nearly 2 years. Air France 447 had been found. The wreckage was only about 6.5 nautical miles from its last reported position. It was sitting in a water depth of 3,900 meters in a relatively flat part of the seabed. The debris field was small, only about 600 meters long by 200 meters wide. Among the wreckage lay more casualties of Air France 447. Over the coming days, the autonomous underwater vehicles were sent to the seabed to scour the area. They would hover about 10 meters above the seabed and take extensive photographs of the wreckage. In all, the AUVs took about 85,000 photographs, which in combination with further side-scanning sonar built up a complete image of the debris field. The final stage of the BEA's search for Air France 447 was Phase 5, involving the recovery of the aircraft's wreckage and the bodies which had been found to the surface. On the 26th of April, a vessel designed for laying subsea cables, the Ile de Seine, arrived. It was equipped with an ROV capable of operating at the extreme depths required, and capable of lifting the heavy components of the aircraft such as its engines. On the 1st of May, the digital flight data recorder was discovered and brought to the surface. The following day, the cockpit voice recorder was also found. Both units were ferried under judicial seal to the port of Cayenne before being flown to Paris for examination. In the meantime, investigators removed aircraft components from the seabed which might help them in understanding the circumstances of the accident. This included the avionics bay and the aircraft's engines. Investigators were not able to identify any signs of fire or problems with any of the components. It appeared that the engines had been generating full power at the time of impact. Finally, the process of recovering the bodies begins. A total of 104 bodies were recovered from the seabed, bringing the total number of bodies found to 154. 74 of the casualties would never be found. The BEA was able to recover all data from both the cockpit voice recorder and the digital flight data recorder. The story they discover on the flight deck of the aircraft is one of chaos, confusion, and tragedy. With the information available from the aircraft's black boxes, it is now possible to travel back to the 1st of June 2009 and know what really happened on the flight deck of Air France 447. At 1:30 in the morning, Air France 447 is cruising on autopilot above the southern Atlantic Ocean at 35,000 feet. In the cockpit of the aircraft at this moment are two people. The captain, 58-year-old Marc Dubois, is an Air France veteran, with just shy of 11,000 flying hours. To date, he has carried out 16 rotations through the South American sector. Joining him on the flight deck and flying the aircraft at this moment is First Officer Pierre Cédric Bonin, age 32. Despite having only a third of the flight hours of the captain, Bonin nevertheless has a significant level of experience at just under 3,000 hours. As we discussed earlier, Air France 447 has just passed a waypoint known as Intol, which sits about 300 miles off the Brazilian coast. Captain Dubois contacts the Atlantico Area Control Center and advises them that they have just passed the Intol waypoint, and their next waypoint will be Salpu in about 15 minutes, followed by Oraro 15 minutes after that. The Atlantico controller advises Air France 447 to contact Dakar, the next control centre, after passing waypoint Tassel. Captain Dubois asks Atlantico to perform a test on a piece of radio equipment. With that check successfully completed, the crew are advised to maintain their altitude of 35,000 feet. Captain Dubois acknowledges the communication. This is the last voice transmission received from Air France 447. Bonin attempts to communicate with the aircraft's next area control centre, Dakar, sitting on the opposite side of the Atlantic Ocean in Senegal. Instead of attempting radio communications, Bonin attempts to make contact using ADSC. ADSC stands for Automatic Dependent Surveillance Contract. Because aircraft know where they are on the planet thanks to GPS, air traffic controllers do not need to rely on radar. Instead, the aircraft can tell controllers where it is. This particular method of automatic dependent surveillance requires a contract between the aircraft and the Area Control Center at Dakar. Essentially, this means that the aircraft's identity and flight plan is already logged into Dakar's systems before the aircraft makes contact. Unfortunately for Air France 447, no flight plan has yet been created for the aircraft because Atlantico has not shared the information with Dakar yet. As we discussed earlier, the air traffic controller at Dakar interrupted the controller at Atlantico before contacting him again later. When Atlantico finally does share the information with Dakar, Air France 447's ID is recorded incorrectly by the Dakar controller, so when the aircraft again tries to make contact using ADSC, the communication still fails. Air France 447 has entered an area known as the Intertropical Convergence Zone. This area on the planet, which surrounds the globe at the equator, is a point where the northeast and southeast trade winds converge. The hot air and warm water at the equator causes humid air to rise. When this water cools, it falls in the form of almost perpetual thunderstorms. The air is prone to turbulence and requires care by pilots to navigate. Bonin adjusts the aircraft weather radar to a shorter range and notes a significant build-up of weather ahead. Because the autopilot is flying the aircraft, Dubois and Bonin can concentrate on navigating the weather which lies ahead of them. Tonight, the air at 35,000 feet is unusually warm, 12 degrees more than what would normally be expected at the aircraft's current altitude. Bonin states to Dubois it would be best to climb over the weather. Captain Dubois does not appear concerned by the weather, and states that if they were still in bad weather at 36,000 feet, their manoeuvring options would be even more limited than they are now. The warm weather and the weight of the aircraft, still heavily laden with fuel, does not make climbing possible at this time. The Airbus's systems take data on wind speed and direction, outside temperature, and weight of the aircraft to calculate two flight altitudes, optimal and rec max. The optimal altitude will enable the aircraft to cover the distance at the lowest cost to the carrier. The rec max, or recommended maximum altitude, is the maximum altitude the aircraft can be operated at safely. At this time, the rec max and optimal figures are both the same, in the region of 37,000 feet, but pilots normally leave a margin for safety, and for this reason, the aircraft does not climb any higher. One might imagine that the pilots could split the difference and climb to 36,000 feet. However, this would not be a standard altitude for the aircraft to fly at. As a rule, aircraft travelling east to west travel at even flight numbers such as 34,000 or 36,000 feet. Aircraft travelling west to east, like Air France 447, operate on odd flight levels like 35,000 and 37,000 feet. Bonin discusses the possibility of requesting a non-standard flight level of 36,000 feet, but Dubois states that they should wait a while to see if the turbulence subsides. As a consequence, the aircraft stays at the same altitude and enters a layer of cloud and associated turbulence. As the aircraft travels through the clouds, the cockpit is illuminated by a bright blue light, a phenomenon known as St. Elmo's fire. The difference between the high voltage contained within the thunderclouds and the low voltage below causes the air to ionize into blue plasma. 7 minutes later, the turbulence stops. It is at this point that Captain Dubois decides to take his rest stop. Because the total duty time for the journey across the Atlantic exceeds the maximum time any two pilots are allowed to fly, an additional pilot is required. This enables each of the pilots to take a rest during the flight. Captain Dubois makes his way to the rear of the cockpit, where the A330's rest area is located, and knocks on the door to the crew rest compartment. The man he is waking is First Officer David Robert, aged 37, with 6,500 hours flight experience. Captain Dubois will take the second rest, while First Officers Robert and Bonin will continue the journey. Once Robert is ready, Bonin briefs him on their current situation. With the briefing complete, Dubois makes his way to the rest area, leaving Robert and Bonin to command the aircraft. At 2:06 a.m., the aircraft is reaching waypoint Oraro and entering into another area of turbulence. Bonin contacts the cabin crew and tells them that they will soon be entering an area of turbulence and it would be advisable to sit down. Robert notices a significant area of weather ahead and advises Bonin to turn their heading slightly to the left to avoid it. As the aircraft continues, the temperature in the cockpit suddenly increases even further, and the smell of ozone fills the cabin due to the strong electrical charge in the air. Bonin is not familiar with this phenomenon, and initially believes it is due to Robert adjusting the air conditioning. At the same time, ice crystals start to impact on the aircraft as it continues to travel through the layer of cloud. These crystals are known as graupel, and occur when a layer of precipitation forms around snow and freezes. As the graupel batters the front of the aircraft, the small crystals begin to accumulate in the pitot tube, which faces forward into the airstream, blocking the flow of air. The pitot tubes are heated, but it will take some time for them to melt the pellets and drain the water. As a consequence, the speed for the pilot's instruments become unreliable. Suddenly, an alarm can be heard in the cockpit, known as the cavalry charge. This indicates that the aircraft's autopilot has disconnected, and the pilots must manually fly the aircraft. We know this is due to the speed readings on the different systems disagreeing, but for Bonin and Robert, who were concentrating on navigating the area's weather, this is a complete surprise. The aircraft's autothrust also disengages, requiring the pilots to control the aircraft's throttles manually. Bonin tells Robert he has the controls and takes hold of the aircraft's flight stick, which is attached to the right armrest of his seat. Since it is almost completely dark outside, Bonin must rely on his instruments, in particular his primary flight display, to fly the aircraft. The primary flight display contains the aircraft's speed and altitude at each side of the display. In the centre is an attitude indicator, which tells Bonin the attitude of the aircraft relative to the horizon. This instrument is crucial when flying either at night or in situations where the horizon is not clear. Overlaid on the artificial horizon is the flight director. By aligning the aircraft's attitude with the attitude shown on the flight director, the aircraft will follow a predetermined flight path, such as maintaining a specific altitude. With the autopilot disconnected and the turbulence the aircraft is flying through, Air France 447 begins to bank to the right. Bonin counters this with an input on the flight stick to the left, while at the same time pitching the aircraft's nose up. However, Bonin does not yet realise that the aircraft has transitioned to alternate law, amplifying the movements he makes with the flight stick. This, combined with Bonin being startled at the autopilot's disconnection, means that the input on the stick to counter the roll to the right is excessive and causes the aircraft to bank too far back to the left. Bonin makes a number of alternate inputs, with the aircraft rolling alternately left and right until he finally has it flying straight once again. More concerning than this, Bonin has also pulled back on the stick, putting the nose of the aircraft up and holding it there. This causes the Airbus to start to lose speed and gain altitude. It is likely that Bonin made this input as a consequence of the altitude reading suddenly dropping. This was not a real drop in altitude, but was brought about by the blockage of the aircraft's pitot tubes, upsetting the total pressure reading.
Stalled.
The cockpit is filled with a number of warnings, including the C chord, which is a continuous note warning the aircraft is in an unusual attitude. A stall warning also sounds briefly. At 35,000 feet, the aircraft's flight envelope, the combination of speed, altitude, and angle of attack which the aircraft can safely fly at, is very small. Robert, sitting on the left side of the cockpit at night time, is not able to easily see what Bonin is doing with his side stick. Unlike in other commercial airliners, such as those designed by Boeing, which have a large centrally located control yoke, the Airbus only has a small side stick. Bonin's side stick is sitting on the right side of the cockpit, making it even more difficult to see. He is therefore unaware of the forceful movements Bonin is making with his controls. The two sticks are also not mechanically linked, so Robert's side stick does not move in concert with Bonin's inputs. Almost simultaneously, both pilots notice that they have lost the speed readings on their instruments. It is at this point that Robert notices that Bonin is climbing the aircraft. He tells Bonin to stabilize the aircraft, pay attention to his airspeed, and descend. Bonin agrees. He makes a number of inputs which lowers the aircraft's pitch slightly, but the aircraft is still climbing. In spite of lowering the nose, about 30 seconds after the Airbus's autopilot has disconnected, the aircraft has already climbed 2,000 feet to 37,000 feet and is still climbing. The C chord continues to sound, saturating the cockpit environment, which is not helping the pilots concentrate. 30 seconds after the autopilot disconnected, the speed readings on Robert's display becomes valid again. The aircraft's speed has fallen by about 50 knots to 223 knots. Robert, realizing the seriousness of the situation, tries to summon Captain Dubois from the rest area by pressing a call button. A series of nose-down inputs by Bonin has arrested the climb the aircraft is in, and the situation looks to be improving. Airspeed has stabilized, and the rate of climb is now much lower. However,
Stalled.
Suddenly the stall warning triggers again, causing Bonin to pull back on his side stick. The altitude of the aircraft begins to rise again. Speed continues to fall. At this point, the heaters in the pitot tube are able to melt the buildup of Graupel for Bonin's instruments. The measurement system for both Bonin and Robert's displays are now fully functional, and will remain functional for the remainder of the flight. With the aircraft's nose still pitched upwards, and its speed decreasing, the Airbus begins to buffet. Buffeting is a phenomenon experienced as the airflow over the wing begins to be disrupted. Buffeting provides the pilots with a final warning before the aircraft enters into a stall. It does not rely on any instruments, since the phenomenon comes from the aircraft's airframe itself, and will be present even if all instruments are inoperable. Neither Bonin or Robert acknowledge the sound of the stall warning, nor the buffeting. Bonin does, however, set the aircraft's engines to their takeoff go-around power, a preset which delivers a high level of thrust. The two General Electric CF6 engines spool up and roar louder than before. Just 1 minute after the aircraft's autopilot disconnected, Air France 447 is approaching an altitude of 38,000 feet, 3,000 higher than when it started. The rapid reduction in speed is accompanied by an increase in the angle of attack as the nose begins to point higher and higher. The Airbus is now well past the recommended maximum altitude of 37,000 feet. The engines struggle to generate thrust, and the wings struggle to generate lift in the thin air until their combined efforts can no longer support the aircraft. Under its own momentum, the Airbus continues to climb for a few seconds longer. The aircraft loses all of its kinetic energy as it is converted into potential energy, until the point was reached when the aircraft unavoidably stops climbing and starts to descend. The crew watch as the aircraft's altitude goes into free fall, plummeting at an incredible rate of 10,000 feet per minute. The shrill sound of the stall warning, combined with the synthetic voice, fills the cockpit.
Stall, stall.
It is interspersed with the C-chord attitude alert. Bonin states he does not have control of the aircraft at all. As Air France 447 falls, it develops a bank to the right. Robert announces he is taking control of the aircraft. He pushes a button on his own side stick, which takes control priority, and begins making inputs to the left to try and counter the bank. But with both the wings stalled, the plane is not responding. Almost immediately, and without warning, Bonin takes priority back from Robert. The chain of command within the cockpit is beginning to break down. This could partly be due to Captain Dubois not indicating who is in command of the aircraft while he is on his rest break. At this moment, Captain Dubois re-enters the cockpit to the sound of the stall and attitude warnings. He asks the two pilots, "What are you doing?" Robert and Bonin both tell Captain Dubois that they have lost control of the airplane and they do not know what is happening. They tell him they have tried everything. The aircraft is falling at 10,000 feet per minute, but is travelling with its nose pointing upwards and its engines generating a high level of thrust. It's therefore difficult for Captain Dubois to determine why the plane is falling. The cockpit is filled with the intermittent sound of the C-chord attitude warning and the aircraft stall warning. Very shortly after Dubois comes into the cockpit, the speed readings on the aircraft become invalid. Air France 447 is travelling so slowly that the instruments can no longer reliably produce a speed that can be accurately measured. With no valid speed reading, the measurements disappear on the primary flight display, and the stall warning sound stops.
Stall, stall.
The pilots discuss the invalid speed readings. Bonin states he believes that they have a high level of airspeed, and begins to deploy the aircraft speed brakes before Robert tells him not to do it. Robert tells Bonin he is climbing, and in response Bonin pushes the nose of the aircraft down. This causes airspeed to build up, until the reading becomes valid once again. As soon as the airspeed becomes valid, the stall warning again sounds.
Stall, stall.
This is in contrast to what the pilots would expect to be happening. From the beginning, every pilot is taught that from the onset of a stall, their reaction is to point the nose down, but the aircraft is telling the pilots something different. Every time Bonin lowers the nose, the stall warning sounds, and Bonin instinctively pulls the nose up again to make the warning stop.
Stall, stall.
The pilots talk in confusion, trying to determine whether they are climbing or descending. The aircraft is now passing 10,000 feet and still falling. Both Captain Dubois and Robert both shout at Bonin to climb the aircraft. Bonin then tells them something that suddenly brings clarity to the situation. He tells the pilots that he has had the nose up the whole time. It appears that Captain Dubois finally realizes what has been happening. Dubois shouts, "No, no, don't climb, descend." Robert announces he is taking control of the aircraft and pushes the nose of the Airbus down.
Dual input.
As Bonin is still moving his side stick, a dual input warning sounds in the cockpit for some time before Bonin eventually gives up the controls.
Dual input.
As the nose lowers, the speed of the aircraft starts to build once again, and the stall warning once again sounds. The aircraft is still plummeting. At 5,000 feet, the A330's ground proximity warning system begins sounding. This system is designed to inform the pilots they are about to either strike the ground or an obstacle. In this case, the GPWS warns the pilots of their excessive rate of descent, calling,
Sink rate. Pull up. Pull up.
Robert does as the system instructs, and again pulls back on the controls. Bonin joins him in pulling back on the controls, but they don't have nearly enough speed to break out of the stall. Bonin states, "Damn it, we're going to crash. This can't be true. But what's happening?" Captain Dubois orders 10 degrees of pitch attitude. A second and a half later, the recording stops. Air France 447 impacted travelling at nearly 11,000 feet per minute, or 60 metres per second, and travelling at only 106 knots in an almost flat attitude. The Airbus A330 shatters on impact. The heavier and less buoyant components, such as the engines, sink below the surface. Other debris, and some of the passengers, remain on the surface. From the disconnection of the aircraft's autopilot to the aircraft crashing into the southern Atlantic took approximately 4.5 minutes. The BEA released a total of 4 reports on the accident of Air France 447. The first and second detailed the ongoing search efforts before the aircraft had been found. The third interim report was released after the discovery of the wreckage and analysis of the cockpit voice recorder and flight data recorder. The report was highly critical of the actions of the pilots, especially Bonin. The mainstream media picked this up, and Bonin in particular was widely vilified. A popular article which has been read by many who wish to understand more about Air France 447 was written by popular mechanics. The article portrays the pilots as incompetent and ignores basic questions such as why Bonin may have been pulling back on the flight stick in the first place. Far from being the inexperienced, foolish pilot relying on the aircraft to fly itself, which he was portrayed as in the media, Bonin was nothing of the sort. As well as flying commercial airliners, Bonin was also a private pilot and held a glider pilot's license. This was not a man who did not understand the effects of controls on an aircraft. Bonin was, however, a man who was probably out of practice at hand flying the A330. The majority of his experience of hand flying the aircraft would have been during takeoff and landing. He had very little experience and was provided little training on how to hand fly the aircraft at altitude. In a split second, Bonin was required to transition his focus from monitoring weather radar and the aircraft systems to basic stick and rudder flying with incredibly small tolerances given the aircraft's altitude and speed. Over time, a more balanced story of the demise of Air France 447 has begun to be told. The BEA's final report on the crash of Air France 447 moderated their initial blame on the pilots and turned their attention more to the interface between the pilots and their aircraft. First, the investigators drew issue with the aircraft's ECAM. ECAM stands for Electronic Centralized Aircraft Monitor, and as the name suggests, provides a single source of information on the status of a variety of the aircraft's systems. Immediately after the disconnection of the aircraft's autopilot, the ECAM displayed a barrage of messages. While some of the messages were useful, many were not in determining what was wrong with the aircraft and what the correct approach to take was. More importantly, the investigators drew issue with the aircraft's flight director. The Airbus's autopilot and autothrust were disconnected when valid airspeed readings were lost and could only be reactivated by pressing a specific button. However, the display for the aircraft's flight director would periodically appear and disappear on Bonat's primary flight display during the accident sequence. Even as the aircraft was stalling, the flight director was still instructing Bonat to climb the aircraft. Whenever the flight director display appeared again, Bonat would try to pitch the nose of the aircraft up and follow its directions. The very fact that the flight director was telling Bonat to climb the aircraft might have led him to believe that the aircraft couldn't be stalling. There is also a good chance that neither Bonat nor Robert believed it was possible the Airbus A330 could really be stalling as a consequence of their inputs. During the accident sequence, apart from the synthetic voice announcing the stall, the message never appeared to be acknowledged by the pilots. The word stall was never mentioned once. In normal law, the aircraft's flight system would not allow inputs that would permit the aircraft to stall. As we discussed earlier, the transition to alternate law removed these protections. Although Robert announced that the aircraft was in alternate law, the implications of this change may have been lost on the two pilots, given the tense situation they found themselves in. Only a small message on the aircraft's ECAM informed them of this change. Even the design of the aircraft's primary flight control, the side stick, was called into question. Bonat's inputs could not be easily seen by Robert in the dark cockpit. Furthermore, the controls are not mechanically linked. Had there been a mechanical linkage, Robert would have been able to better see the extreme inputs Bonat was making on the controls. The loss of Air France 447 is perhaps the defining air disaster of the 21st century. It highlights the importance of the interface between an aircraft and its pilots. We live in an era which has seen huge leaps forward with automation, even in our own personal lives, but the systems are not perfect. Aircraft are easily capable of performing entire flights through automation of tasks such as takeoff, cruise, and landing. But when that automation fails, the pilot can be thrown into the midst of a complex and challenging situation without warning. Indeed, the very situations where automation will fail are in some of the most extreme situations which the aircraft designers could not predict. The very automation which removed so much of the actual flying work from the pilots and gives it to the aircraft degrades a pilot's ability to fly the airplane in such conditions through a lack of practice. Improvements have been made to the safety of the aircraft themselves. The pitot tubes, which had been shown to be prone to icing numerous times, were replaced with more reliable ones. But one of the most unsettling things about Air France 447 is that there is little that has really been done in the aftermath to stop such an accident happening again. In the aviation world, the puzzle of the interface between human and machine is one that's still to be solved. Thank you for listening to the latest episode of Inside the Black Box. The podcast has grown significantly over the last month, and that is down to people like you recommending it, so thank you very, very much. Until the next time.